All right, class. So let's continue talking about spectroscopy. So again, going back to why we're talking about this, if I have a flask and I have a solution in here, I have no idea what it is, I can use spectroscopy to figure out the structure of my compound here. We've talked about IR, you got that down. Now we're going to talk about NMR, nuclear magnetic resonance. Now let's go back to the electromagnetic spectrum. Remember this? I put this up when we were talking about IR. You learned this in Chem 1A. Different lights have different energies, and these are the type of lights that we have. Now for IR, infrared was the one that we use to excite the vibration of covalent molecules. Now, what are we going to use for NMR? Before I tell you that, just one more time to make sure everyone is on the same page, and remember your Chem 1A. So radio is the lowest energy and gamma ray is the highest energy. So as you go left to right, the energy increases. This is why when you go to a dentist to take an x-ray of your teeth, they usually put a lead shield on you, right? Because these are high energy. You want to avoid it. You want to avoid the sun. These are high energy. But over here, these are kind of low energy. All right, so for NMR, which one are we going to use? The NMR, we're actually going to use the radio energy. That's such a low energy. It's just enough to change the nuclear spin of some element. And we'll talk about that in 1 second. Now, the other thing I want to kind of talk about, and this is like to make sure you remember your Chem 1A. So we said as you go left to right, the energy increases, right? Now, what happens if the energy increases? Look at these equations for light. If the energy goes up, what happens to the wavelengths? The wavelengths goes down. They're inversely proportional. If the energy goes up, what happened to the frequency? The frequency will go up. So as you go left to right, increasing the energy, but that means it's going to be shorter wavelengths, but the frequency is also going to increase because wavelengths and frequency are inversely proportional. Energy and wavelengths are inversely proportional. Energy and frequency are proportional, not inversely. So far, so good? Okay, this is a lot of fun to make sure you remember your EM spectrum. All right, so let's go back to the NMR. So we said radio energy is what we're going to use, but this is a low energy. It's just enough to change the nuclear spin of some element. It's not enough at all to excite the electron, or it's not even enough to cause the vibration of covalent molecules. Now, so I said it's just enough to change the nuclear spin of some element. The two elements that we are interested in is proton and carbon 13. Those are the isotopes that we are interested in for NMR. Okay. Now carbon 13 is not the main isotope, right? We have carbon 12 and we have carbon 13. So carbon 13 is not as abundant as carbon 12. And then proton is 1. So these are the two isotopes we are interested in. So far, so good. Okay. Now here is a requirement. Here is the requirement. Again, we're gonna shine radio energy that's just enough to change the nuclear spin for some element. The two elements we're interested in are these two elements. Carbon 13 and proton. Now again, carbon 13 is not the main isotope, right? Carbon 12 is a lot more abundant than carbon 13. So here is a requirement. You guys ready? I'm actually going to write it down to make sure everyone's on the same page. Here is a requirement. To see atom, if you want to see an atom with NMR, if we want to see an atom with NMR, here's what we need to do. We need to have nuclear spin. Because remember, when you shine the radio energy just enough to change the nuclear spin of some element. Now, so even to see an atom with NMR, you need to be able, when you shine the light, you have to have a nuclear spin. And what do I mean by that? I mean, I need quantized quantum spin. Quantized quantum spin number. Again, you have to kind of go back to Chem 1A. Now, if the quantum spin number is 0, then you will not see it with NMR. Okay. Again, kind of going back to Chem 1A, what we talked about, but what I would just want you to get out of this right now, that no, you cannot see everything with NMR, right? If you want it, in order to see an atom with NMR, that atom needs to have a nuclear spin. If the quantum spin number is 0, you will not be able to see it. That's all I really want you to know, okay? Just kind of the overall idea that if your quantum spin number is 0, you're not going to be able to see it. So not everything can be seen by NMR. So far, so good? Okay. Now, let's go back to proton. Proton spins on its axis. Okay? And what that does, that will create a magnetic field. It's a little physics we're gonna go over. I'm not happy with that. So here's a way to think about proton. Okay, I'm actually gonna draw a proton like this. This is gonna be my proton. Now, why am I drawing it this way? Here's the way to look at proton. Okay, proton nucleus is like a tiny magnet bar. So proton nucleus is like a tiny magnet bar. Magnet bar. Oh my god. Spelling on this board is hard. So proton nucleus is like a tiny magnet bar. So imagine like here's a proton, there's a little magnet bar inside it. Everyone's seen it has a magnet bar, right? There's like a red part and a black part. So there's like a tiny magnet inside the proton nucleus. Okay? And they are randomly oriented. And these are randomly oriented. You write it down too. Randomly oriented. Okay, we're good so far. And this is ugly. Let me make it a little bit prettier. There we go. Okay, so think about the proton nucleus is like a tiny magnet bar. Think about it, we have this magnet bar inside the proton, inside the hydrogen. Okay, and these are randomly oriented. All right. Now, NMR is like a giant magnet. That's how I want you to look at NMR. NMR is a giant magnet. That's the one I want you to think about it. A giant magnet. So, yeah, NMR is like an external magnetic field. Okay? It's like an external magnetic field. So if we put the NMR, which is like a giant magnet, next to these protons, there's two ways they can be oriented. With the magnetic field or against the magnetic field. Okay? Now, I'm going to go slow because I know these are a lot of physics that I've been trying to avoid, right? So here is our external magnetic field, okay? Here is our external magnetic field. And think about NMR as a giant magnet. Now, all these protons that are randomly oriented, if you put a magnet next to those, there's two ways they can be oriented: with the magnetic field or against magnetic field. So they're either going to be with the magnetic field or against magnetic field. Okay. So far, so good. Okay. All right. I'm going to go over it one more time. So NMR is like a giant magnet. So if you take an NMR, if you're near an NMR instrument and you have anything magnetic on you, that's bad, because it's like a giant magnet. It's going to attract it. So NMR is a giant magnet. Here's our magnetic field. Now you have these protons that we said, think of proton as having a tiny magnet bar inside. So once you put these next to a magnet, there are two ways it can be oriented. They're either going to be with the magnetic field or you're going to be against the magnetic field. Now, if you're aligned with the magnetic field, that has a lower energy. And if you're against the magnetic field, that has a little bit of more energy. So far, so good. Okay, beautiful. Now, here is the next part. So, we said that here is our magnetic field, okay? And we said that if the proton is aligned with a magnetic field that has a lower energy, okay? Now, what happens if we apply energy? We're going to apply energy, right? What kind of energy we're going to apply? Radio energy. Is going to absorb this radio energy, and then the spin is going to change. But remember, this is a lower energy. This would be a higher energy. This is a lower energy. This would be a higher energy. Okay, that's why I put a little bit up, but I don't know if I did a good job on that or not. Probably not. So this is a low energy. This is a higher energy state. Okay, all right. Are we good so far? So let's go back again. So here's the thing: NMR is a giant magnet. The proton, think about them as like little magnets, right? They have a little magnetic bar inside them. When you put it next to an NMR, it's either going to be with it or against it. If you align with it, that has a lower energy. Okay? Now, if you apply energy, if you apply radio energy, they're going to absorb that energy and is enough to change the spin, right? We said the radio energy is low, but it's just enough to change the nuclear spin for some element. So when I apply energy, the energy, radio energy, okay, and this is a radio energy, the radio energy is enough to change the spin. This is a low state, but I apply energy, I can make it to go against the magnetic field to be higher energy. So far, so good? Okay. Now, is it going to stay this way? Probably not. It will go back to the low energy state, right? It will go back to the low energy state. All right. So far, so good? All right. I want to rewrite this to just make sure you really, really understand this. So let's rewrite this and summarize this one more time. Our NMR is a giant magnet and it has a magnetic field. It has a magnetic field. Some of the protons, they are going to be aligned with a magnetic field. Okay? And what that means is they're going to be a low energy. But if you shine radio energy to it, if you apply energy to it, they can absorb the energy and then change the spin. So they're going to absorb the energy, and then you can change the spin. You go to the higher energy spin. You can have it to be against the magnetic field, which is higher energy. So when you go up, you absorb the energy. Now, is it going to stay there? It's not going to stay there. It's going to come back to the low energy state. When that happens, it's going to release energy. So absorb the energy, and here is you're going to be able to release energy. So you're going to apply energy, it's going to absorb it, it's going to go to the higher energy state, right? But it's not going to stay in a higher energy state. It's going to come back down. And when it comes back down, it's going to release energy. Absorb energy, release energy. Okay. Now, over here, this is the energy difference, right? You got energy, you go up, you're not going to stay there, you're going to come back down. It's like pushing someone on a swing. You push someone on a swing, they're going to go up. Are they going to stay there? No. They're going to come back and they're going to release that energy. So when they release that energy, what's going to happen? The detector is going to measure this energy. So the detector is going to measure this energy. The detector is going to measure this energy. Yeah? Okay. And the detector, this energy difference is going to be detected by a detector, and it's going to be recorded and measured in hertz. Now, to make sure that you really understand this, I'm actually going to write this down. Okay? So, what we're going to have a detector. And the detector, what's going to happen, the frequency of the radiation used for this spin flip is measured, and is measured in hertz. Again, it's nothing fancy. Think of the swing. You are low energy, you can apply energy. You can push someone to go higher up. But when you push someone on the swing, they're not going to stay there. They're going to come back down and then release energy. And the detector is going to measure this energy in hertz. The detector is going to measure this energy in hertz. Okay? So this energy is measured in hertz. Again, you apply energy, absorb it, and then what's going to happen, you're going to have a spin flip, and then you're going to go to higher energy state, but you're going to come back down eventually, and the detector can measure that energy difference. Yeah? All right. Beautiful so far. Now, why this all matters, right? Why this all matters. And here's the key, why this matters and why NMR is going to work. Here's the key. You ready? All protons, I'm actually going to write this down. So all protons do not absorb at the same frequency. Almost the same idea as IR, right? Not everything did the vibration at the same frequency. So all protons do not absorb at the same frequency. Now, protons in different environment, and we talked about this in the very first lecture, what that means. Protons in different environment, if you don't remember that, go back to that lecture. Protons in different environment absorb at slightly different frequency. I know I went really slow in this lecture, but I want to make sure you understand the different frequency, and that is key. Now, because proton in different environment absorb at a slightly different frequency, what that means is they're going to be distinguishable by NMR. So they're going to be distinguishable, hopefully I spelled it right, by NMR. They're going to be distinguishable by NMR. Now I want to give you an example of what I mean by that. And this is an example that we used in that lecture when I went over different types of NMR, different types of proton. So here is a compound that I have, right? If I put a hydrogen here, there is 3 hydrogen here, there is 2 here, and there is 2 here. And if you remember, we said how many different sets of hydrogen do we have? Now, in that lecture, we said, okay, these hydrogens are in the same environment, right? I'm going to call it A. These hydrogen on top, they're also all these 2, same environment, I'm going to call them B. But we also said that these are the same as A because they have the same neighboring, right? They have the same neighboring. So NMR will be able to distinguish A from B. NMR will be able to distinguish A from B. So far, so good. Okay, now let's go over what an NMR spectrum looks like. We know what an IR spectrum looks like. Now let's go over what an NMR spectrum is going to look like. Let's look at this one. So you already know IR, right? So when you look at this, you go, this is a sample spectrum. You go, okay, I know what this is. This is IR. It's pretty cool. Now this one right here, that is Proton Nmr. That is Proton Nmr, okay? And this one right here, this is Carbon Nmr. This is Carbon 13 Nmr. Now in this class, we are going to focus on Proton Nmr. Okay, so here's the IR. You knew what it looked like before. Here's another example of IR spectrum. And for IR, what we look at wave number, right? So for IR, we look at wave number, which is this. No, I did not do that correctly. There we go. There we go. Now for Proton Nmr, what we look at ppm. Okay, we look at ppm. That's the chemical shift. So for IR, we have wave number. For Proton Nmr, or Carbon Nmr, we have ppm, parts per million. So far, so good? Okay. All right, beautiful. Now, let's get more into this Proton Nmr. But the point of this page is like when you see a spectrum, you go, oh, this is IR. Oh, this is Proton Nmr. Oh, this is Carbon 13 Nmr. I want you to be able to know right away what you are dealing with. Now, let's talk about this Proton Nmr, okay? So let's talk about this Proton Nmr. So I said that IR is, we use wave number. For Proton Nmr, we use ppm. You also call it chemical shift. So the chemical shifts are in ppm, parts per million, okay? And again, this is a symbol for it. All right. Now, starts from zero, and it goes to around 12 ppm. So you start from 0 ppm to 12 ppm. So as you go from right to left, the chemical shift are going to increase, right? You're absorbing more energy. So what is at zero? At zero is TMS. At zero is TMS. Now, what does that mean? Basically, TMS which is at zero, it's a reference peak. So TMS is a reference peak, and all peaks are relative to their reference peak. We're good so far? Okay. So one more time. Here is my Proton Nmr. It goes from 0 ppm to 12 ppm. Okay. Now 0 is my reference peak, which is TMS. I use TMS as a reference peak. And all the peaks are relative to the reference peak because you need a reference to compare it to. Here is an example of the sample spectrum. So I want you to look at this. So when you look at this, right away you're going to say, oh, I know the one on top. That's IR. Perfect. The one in the middle, this is Proton Nmr. And the one down here, that's carbon 13 NMR. That's carbon NMR. Okay. Now in this class, we're going to focus on IR and proton NMR. Not so much carbon NMR right now. So when you look at the IR, you know what an IR spectrum look like. And IR, what do you use? For IR, you use wave number. Wave number is what you use for IR to say what the peaks are. So wave number, let me draw this a little bit nicer. So we use wave number, right, to figure out what we have. Now here's a proton NMR, right? So here's a wave number for IR. Here's the proton NMR. Now what we use ppm. We use parts per million. We use ppm, okay? And is a delta scale. Oh my goodness, so hard to write in this. Is a delta scale. So IR was a wave number and proton NMR is ppm. So far so good? Alright. Now let's look at this proton NMR a little bit more closely. So here is proton NMR. And proton NMR, when you look at the spectrum, it usually goes from 0 to about 12. Okay. Now this is, we call this chemical shift. And we just said that it is in ppm, parts per million. It is in ppm. All right. So as you go from right to left, the chemical shift is going to increase. Now you see there's a 0 peak over here. That's a reference peak, and the reference that we use TMS, tetramethylsilane. Tetramethylsilane. We use TMS, and TMS is our reference peak. So we measure the TMS and we say, okay, we're going to set the TMS to be 0. So all the peaks are relative to the reference peak. So far so good. So you have a TMS and then you go, okay, so TMS, I'm going to set this TMS proton be 0. That's my reference. And all the peaks are relative to the reference peak. So far so good. And just for fun, TMS, you have a silicone and you have TMS is tetramethylsilane. So far so good. All right, perfect. So our reference peak and all the peaks are relative to that reference peak. Yeah, beautiful. Now, as you go from 0 to 12, when you're more on this side, we call this upfield. So we call this part upfield. And when your ppm gets larger and larger, we call this part downfield. So when we talked about it, we go, yeah, the NMR, look at the upfield region, look at the downfield region. That makes it sound cool, right? Yeah, it's like you're an organic chemist when you talk like that. So upfield and downfield. And also, this part, the upfield, is shielded. I'll talk about what that means. And the downfield is de-shielded. So these are the cool terminology to use. If you want to sound cool, you're going to use it. Upfield, downfield, shielded, de-shielded. Now let's say why that is. What does it mean by shielded and de-shielded? And why is it if you are lower ppm, you're shielded. If you're higher ppm, you are de-shielded. So let's go over that so you know exactly what we mean by that. What I'm going to do, I'm going to draw a compound. Let me draw this. Here is a carbon attached to 3 methyls. Okay. Now right here, this hydrogen over here, okay, it has an electron cloud around the nucleus. Do you agree? So this hydrogen over here, you have an electron cloud around the nucleus. Now what happens is this electron cloud actually shields the proton. So it's kind of shielding the proton. So again, you have an electron cloud around the nucleus. This electron cloud is shielding, is protecting the proton, so it's not going to feel the magnetic field as much. It's not going to feel the magnetic field as much. And because it doesn't see the magnetic field as much, it's going to have a lower frequency. You got that good so far? So what that means is it will have a lower ppm. I will explain this one more time to make sure you're on the same page as me. So this hydrogen, if I'm looking at this hydrogen on the proton NMR, this hydrogen has electron cloud around the nucleus. Now what that means is this electron cloud is going to shield the proton, so it's not going to feel the magnetic field as much. So you're going to absorb at lower frequency, so you're going to have a lower ppm. So far so good? Okay. Now what I'm going to draw, I'm not going to change, I'm only going to change one thing. I'm not going to change only one variable, not the rest. Now I'm going to put OH here. Okay. And again, we have an electron cloud around the hydrogen. But here's the deal. Now what I have here, I have an electronegative atom. Here I had a carbon. Here I have an electronegative atom. What is the electronegative atom is going to do? It's going to suck those electrons away from the hydrogen, right? It's going to attract the electron toward itself. So now the hydrogen is going to have less of the electron cloud around it. I'm going to explain this again. So here hydrogen had electron cloud around it that was kind of protecting it against the magnetic field. Now here, this hydrogen has an electron cloud, but I have an electronegative atom nearby, which is going to pull the electrons this way. Now if you pull in the electrons this way, so it's going to be a less of the electron density around the proton. Okay, now what does that mean? So now because the electrons again are being pulled away and they're going to go towards the oxygen, so the electron density is going to be lower. So now the hydrogen can feel the magnetic field more because I have less of the electron cloud here because the electrons are being pulled this way. So the hydrogen can feel, can see the magnetic field more. Now what does that mean? So if you can feel it more, I'm going to absorb more frequency. So I'm going to have a higher ppm. So far so good? Okay. Now this is why when you have a higher ppm, we call it de-shielded because the proton is not shielded as much because it doesn't have as much electron density because it's being pulled this way. Now this one right here is going to have a lower ppm, is shielded because again the electron clouds around the nucleus are going to shield the proton from the magnetic field. Sounds good? So this is why when you're upfilled and you have a low ppm, you are shielded. When you're downfilled and you have a high ppm, you're de-shielded because a lot of the electrons are being sucked away and they're going to go towards the oxygen. Yeah? Okay. All right, nice job, very nice job. So this is the concept behind a proton NMR. You see a proton NMR, you're going to look at it's probably from 0 to 12 ppm. That's our chemical shift. And then you're going to have an upfilled, which we call it shielded. And then you're going to have a downfilled, and then we call it de-shielded. And now you know why we call it those things. All right, beautiful. Now, next lecture, we're going to talk about exactly to how we look at the chemical shift, how we look at all these peaks on the spectrum to figure out what our structure is. Nice job today, and we'll pick it up next time. I'll see you next time.